lectures. Okay, if anyone wants to follow along, you are most welcome to do so. And there we go. Yeah, I know it's a little bit wild, but it doesn't hurt. Okay, so last time I had talked some about the general conceptual framework of coverage-based testing. And I had noted that many systems, whether at a high level or at a more detailed level, a level of their glass box implementation, could be characterized as a graph from a coverage perspective. It could be formalized into a model, as we say, by a coverage perspective. And we're going to be focusing for the next two lectures on this issue of path coverage. Here, we conceptualize a system either in the small, like a function, or in the large, like the entire system, as a graph with nodes and edges. I think you folks must have taken 260. So you should know what vertices are and edges, or nodes and transitions, yeah. We're going to be talking about different levels to which we could conduct testing, guided by that model, informed by that model, informed as to what to test to get the greatest bang for the buck. As time allows, we might go on to talk about logic-based coverage additionally, which uses a different type of model. Okay. And I had noted last time that systems at a high level should be able to be conceptualized as sort of a state diagram. Here, the system's in a mode or state, and the transitions between states, perhaps due to user input or due to an event occurring, like arrival of a message, or some sort of alarm occurring, or what have you. And so a system would go from one state to the other. For example, as the user starts entering the PIN, it's in a state of receiving the PIN. It then goes to a state of checking the PIN, for example, etc. And I noted that this sort of testing can occur at different levels. I also noted that these sort of diagrams can be created for a vast array of systems. So not just computational systems like embedded systems such as a ATM machine, an automated teller machine, but also processes involving sort of e-commerce, making an airline ticket reservation, right? Or a process of requesting repairs on a consumer electronic device, such as a computer. I also noted that this sort of path coverage can be applied at the lower level with things like statements within an algorithm, okay? Now, what I want to communicate to you this time is some understanding of the different levels of coverage, the subsumption hierarchy, as we say, by which one level of coverage subsumes. It sort of it includes, but it extends beyond the coverage from another level. So transition coverage tests a broader set of things than just node coverage, okay? So that's one thing I want to communicate. But another key thing, as important, is just the key steps in coverage testing, because it may get you confused if you haven't sorted these out in the head. And this is eminently testable material in pop quizzes and, I might add, in exams. Okay? So there's a few key steps that all the methods will be talked about will consider. A few key steps they'll go through. This includes for path testing, path coverage testing, and for logic coverage testing. The three basic steps here are, number one, we identify the set of things we need to cover. Okay. So maybe it's statements within a program. Maybe it's branches within that same program. Logical branches. Maybe it's something called prime paths. Maybe it's sort of predicates, cases where something is true or false in a certain way. Then we develop a set of abstract scenarios that include all these things. For the ones we're talking about today and next time, here the abstract scenarios are paths, okay? So what we want to cover is statements. And so we figure out paths that will reach all statements. It may not be one, it may be many paths that collectively, you put them together, they cover all those statements. Maybe what we want to cover is transitions. And so we have some paths that go, you know, through the true part of the if statement and some paths that go through the false part. And collectively, they cover all of the transitions. So these are paths through the system that collectively cover all the things we need to cover and do so in a feasible way. They're viable. They go from, say, start to finish. So they're things that could in fact take place, not merely paths that can never happen, but paths that represent sort of reasonable ways through the system. Thirdly, we develop a set of test cases that cover these paths. Okay, now you may wonder about the distinction between 2 and 3. When I'm talking here about concrete test cases, ladies and gentlemen, I'm talking about input. I'm talking about concrete, specific input that will get it to go through a certain path up here. So number 2, we're saying, okay, we need a path that will wind its way through the true part of this if statement and the false one of this later one or something. That's in the second bullet point. We're developing these abstract scenarios, these sort of paths that are gonna reach the statements or that are gonna reach the transitions, the branches that we want to reach. But in the third one, the third bullet point here, the concrete test cases, I've got to figure out input like from the user or test data, you know, read in from a file that will get it to go this way on this path and that way on that you know, if statement, or that gets it to go at least 2 times around the loop for this case to test to the requisite level to realize this path that's wanted. So in short, we have a set of things we want to cover, like statements. We figure out a bunch of paths that when you put them together, they cover all the statements. And then we got to figure out how do we realize that path? What input do we need to the system that's going to get it to follow that path? Does that make sense? Okay, because we're trying to get it to follow these paths so we can cover the statements. Some of you are working with Istanbul, I think, right? I don't know that anyone's using Covertura. There's many packages out there. I think Costello is another one, etc. Blanket.js, I think, is another one. Any case, you may have achieved a certain level of coverage. I think some of you have non-trivial coverage, like upwards of 75%, I think. You should be able to relate to this, right? Because you should be wondering, like, okay, what's the remaining things we're not covering? How could we get it to cover that remaining 25% or that remaining 20%? How are we going to get it to reach this method that's never been reached? We need some sort of input from the user or some sort of something in the database or the calendar of the system that's going to get it to exercise that part of the program, right? We need a set of concrete test cases that will get it to go. Okay, so these test cases are what we'll actually put into our test suite. Some may make it to the regression suite. Some might make it just to the sort of first cut testing suite we undertake manually. Others will be automated for occasional use, but not as part of regression. Okay, so what we're going to be doing with these coverage techniques is finding ways to derive legal paths for the program from start to finish. So exercise what you want to cover. Okay, you want to cover statements? I mean, how can you stand up here and say you've tested your program well if you've never reached, you know, you've never had any test case that reaches these 10 core functions of it. You can't. I mean, it's hard to defend. I mean, how do I know those functions are working properly? Well, I don't. I don't. I mean, they might not be, right? I've never tested them, or even tested them since they've been modified. So the coverage techniques provide us a way of reaching those, of getting there to test these things, okay? And we're trying to find specific test cases that are judicious, that are well chosen, that give us this bang for the buck, a small number of test cases that will get this really good coverage. And there's people working on techniques to, with a minimum number of test cases, realize the coverage. I'm not going to be going into those sort of details. The deal here is, look, we at least want to have really good coverage of our system, right? And we have to plan carefully. Okay, now, a lot of the time this is taking place at the high level. It's taking place at something like this, or something like this, or something like this. And we're trying to make sure we exercise this. We have at least one time where the card's been confiscated, right? At least one time where the card is ejected because you've tried to withdraw too much money. As you can imagine, it's in a bank's interest to say, hey, go away if you're trying to draw out too much money, right? Okay. But these things should also be useful for core algorithms. Several of the projects here, maybe all, several of the projects here have some core algorithms. Core algorithms reasoning about what tests are needed if a person has these comorbid conditions, has these conditions associated with their health, what medical tests are needed, right? Maybe it's core algorithms to perform a principal components analysis. Maybe it's core algorithms for scheduling. Maybe it's core algorithms to determine, to whom a support message should be sent, or what have you. And when we have an algorithm like this, we can often map it out. This happens to be in C. It could just as well be in Java or Swift, or pick your other programming language. And when we have an algorithm like this, whatever programming language it's in, and amongst the common types here, a common object-oriented, imperative, procedural, we can reason about the elements of this in a graph. So we go from something like this to something like that. And I showed this last time. And I talked about reaching these different blocks, which are called basic blocks of the program. Basic because if you start executing here, you're going to execute the whole thing. There's no branch in the middle of it. Modulo exceptions, which I'm not going to talk about here. Okay, but basically, if you're reach one point, you're going to be executing all of these lines of code at the same time. Okay, now in order to realize that, you're going to need test cases. So we'll test this. So this is a CGI encoding function. So sorry, decoding function. So what's going to happen is we feed it HTML or HTTP URLs. And in the encoded element here, and the decoded one will be written to, that's basically a human readable version of that, okay? It will actually be more than human readable. It actually is the URL that will then be accessed, okay? So these are some examples here. So we'll have, for example, a test as part of the URL, the encoded URL, we might have test plus case. What is that going to turn into, in fact? What is that going to unpack to if we decode it from this? What is this going to turn into? Plus turns into what? Space. Yeah, it turns into space. That's right. If we had percent signs, like %20, turns out that's a space as well, because It's hexadecimal character, hexadecimal 20, which is 32, which is space, okay? And in general, you can have encoded HTML things and decoded. And the job of this is to decode. And so we might give it some test cases, particular inputs. Remember, we're talking here about particular inputs. Whoa, in this last section here, we might reason, okay, we want to reach all of these branches. So we reason about paths that go from start to finish that will reach collectively all those branches. So we need at least one path that will go this way, right? We need at least one path that will go this way. We need at least one path that will go this way. Collectively, we have a bunch of paths. And then we might have specific test cases that provide input that will exercise those paths. So, for example, this empty one will go a certain direction. In particular, it will come in here, and if it's an empty string, it's null terminated in C, meaning it ends with the 0 byte. Where's it gonna first branch to? So it comes in A. Where's it gonna go next? B. Then where's it gonna go? It is going to go to, ladies and gentlemen, maybe you've forgotten your C. So what is this while star E pointer checking? Yeah, it's checking, is E pointer pointing to something that's non-zero? And when would it be 0? If it's pointing at the end of a null terminated string, because strings in C end with the 0 character. And so if you reach here, if you have an empty string, it's going to reach here immediately. It's going to go get pulsed, right? This next one, test, where's that going to go? Where's that going to go?
Going to go to C.
Sorry?
So A, B, and then C.
A, B, and then C, because the first thing in it, E pointer is starting, pointing to the beginning of it. The first thing for this test case is it's not the null character. It's not the end of the string. So it's going to go to C. And then from then on, where's it going to go? So we got the next thing. We call it C. Is C equal to plus? Notice the first character plus. It's going to go to D, right? Then we're going to see, okay, is C equal to percent sign? Is the first thing for this percent sign? No. So we're going to go to F, right? And what's that going to do? Well, that's going to just add on whatever character it is. It's not a special character. It's not plus. It's not percent. It's not 0. So it's going to add it on to the decoded string. And then, so it's gone over here to F, and then it's going through down to L, and it's looping back up. So each of these guys is going to lead to a path through the code. Do you understand that? Do you appreciate that? Okay. So these will collectively exercise some set of paths through the code. And if we don't have enough paths, we will add another test case, and we will dream up an input that will exercise that. Ladies and gentlemen, this is much of what I want you to do for ID4. Man, I feel like I should stand up on this and shout it. I want you to, I know you love that too. Especially the recorder on there. But the truth is, I need you to come up with some specific test cases with particular inputs to exercise paths through the system, to try out certain concrete scenarios. For one of the teams, I gave a bunch of scenarios to test, but that's far from, a done deal, because for each of those, you need some particular thing that will be testing it, some particular situation that's going to test it out, right? In order to exercise these paths, you can't just say, make this path happen. You have to give it particular input. And coming up with these inputs is often non-trivial. It requires, you know, okay, how are you going to get it to, for example, go via this path? Okay, you got to kind of trace the logic through. Okay, so we can't have the first thing be 0. And then, you know, if we got to get here, we have to make this branch. So we can't have it be plus. But then we need this one to happen. So we need a percent sign. And then we need 2 hex digits that are valid so that it goes this way. So you got to reason through the code to come up with these test cases. Do you understand that? You got to come up with specific test cases that will accomplish something. Just like you have to come up with specific test cases to achieve boundary value testing or equivalence class testing. You need particular test cases to secure path coverage. Indeed. Okay, so we're going to be trying to go here from sort of long-winded descriptions like you might put into documentation for us to read for the IDs to graphs that you folks would come up with, and then you're going to be reasoning about these graphs. And you can do it for many cases. And it's not perfect, but it captures the essential features of the situation often, or essential features that can then be reasoned about in terms of coverage. Okay. Now, it turns out that it's imperfect, as we'll see. There's cases where the graph, if built naively, it doesn't capture what's needed. Yeah.
Those path diagrams, like you can use those for either like the whole system, or you can use them just for one function.
That's exactly right.
Is there one you prefer?
So I don't want you to do this for all functions, but if you have like a particular important function that's used, it has a particular core role in one of the tasks, then having this for that function would be awesome. But I wouldn't want you to do it for all functions. What I do definitely want is I want to see this for the whole system. Okay, I want to see a graph for the whole system, which shows like the different states or say screens you could be on, or modes that you can be in. You know, you're in a mode where you're setting the columns that you want to display, or you're picking the file that you want to read the data from. And then you're in another mode where you're maybe changing which columns are displayed. You're in a visualizing mode, maybe where you're at a fixed location, you're in a flying mode or something like that. And you can get to one from the other. If you've got a mobile device app, you know, maybe these are screens in the device. You're on one screen, you press a button and it goes to another screen, or it shows an error message. And so I definitely want this for the system as a whole. That is the most important thing, okay? And there may be certain sub-aspects of the system that you also ought to document, like core algorithms. Is that helpful? Yeah, okay. Cool. Okay, so, you know, often this involves taking some sort of high-level description and turning it into some sort of graph. It's not going to be perfect, but it's going to get you much further than just staring at this and figuring out how to test it. By reasoning about it in a model, as a kind of a graph, you can at least ask, okay, how are we going to thoroughly test this thing, right? Earlier, we talked about thorough testing from the perspective of, you know, things like equivalence classes or orthogonal arrays or boundary values. Here, we're talking about thorough testing from a path perspective of Xers reaching different things within it. Each of these are very valuable for creating test cases, but you want to do at least some of this to be sure that you're reaching the functionality of the system, okay? Okay, so I want to remind you, these were the steps we went through, that I talked about going through. We identified the set of things we want to cover. We want to cover screens within the application. We want to cover web pages within the web app. We want to cover, you know, the modes of this system that we can be in interactively. We identify some paths that will take us through those, that will visit all those things. And then we develop some particular input. This concrete input is like very particular things. It's like things the user would enter exactly this. They put in exactly that input, and that will exercise that path. This is not sort of wiggle room, thing. Oh, we put in some string that will exercise. No, I want to know what is the string you will put in. Why? Why do I want to know that? Because where it reaches is often requires some thinking, and coming up with these strings is often non-trivial. So you want to save it away. And because if you want to reproduce a test, you want to know what string was entered. If it crashes, right, halfway through this algorithm, you want to know, well, what was the string I was trying? And to put it into your regression suite, you want to have the string you tried it on, right? And you might not just want one such string. Indeed, often we have a test suite which has different test cases, but it requires a lot of concrete thinking as which particular one to take. To put in place. Okay, so these are the stages we're going through. We're having concrete test cases, so we'll exercise this. Okay, and so we're looking to find a set of specific test cases that will exercise the paths that cover things. So I'm going to start talking now, and it's not going to take that long, but it's going to go into next time, about different levels of testing. And the first I want to start with is node testing. Okay, we talked about this before, right? So here's a system. You have several stages. A stage of having made a reservation, having paid for it, having ticketed it, having used it, or being in a state where it's been canceled by the customer or canceled non-payment. And I noted that if you're thinking about it specifically from the standpoint of these states, you could achieve full coverage with these paths. One, you make a reservation and you cancel it because you never paid for it. It just expires. Right now, you can make a reservation. If you don't pay within a certain amount of time, it's gone. If you work with a travel agent, this is pretty common. Another, you make a reservation and you cancel it, right? That will get us to this canceled state. Otherwise, I can make it, I could pay it, I could ticket it, and I can use it. And collectively, I've reached all these states. All those states have been realized at one point or another. Or maybe I have a situation where I want to test out an IT system that's going to support repair of HP devices or of oscilloscopes made by Tektronix, or of phones that are made by Samsung or what have you. And I have a process they go through, and I want to test the IT system to make sure it works for all the stages of the process, because it's used by the customer and it's used by the repair shops, both sort of locally in the central repair depot and the folks who supply the components, etc. So I want to go through a set of cases that will cover all these different sort of eventualities. So I want to have no maintenance. I want to wait for the pickup. I want to take it to a repair station. It has to go to repair headquarters, and the system should be working during all these phases. And so here we have two cases we might go through. One is, there's no warranty and it goes through a process associated with that. Another is that it's a US or EU resident, probably Canadian is in there as well. And we go through all of these stages here, and it's repaired and returned. So this is another case of node-based testing, vertex-based testing. We're reaching all of these nodes. Does that make sense? Okay, just going through here. This is the simplest and weakest criteria. What test gaps are there? I mean, why do I say it's the weakest? What might be missing here? What things might you miss at a practical level in real code? Yeah. Okay. Good. I like that. That may not be captured well. Another case is, code works fine based on one path through the system, but it fails on another path, right? Maybe one path through the system initializes a pointer. So, you have and I don't know if I've, yeah, here. So suppose I wanted to do state-based testing here. I want to test that I'm reaching every statement here. Okay. So here I assign to some pointer a null value. I say, okay, I'm gonna, for this path, I want to cover this thing inside the if2, so I'll reach that, and then I continue on and reach these later things. That may work perfectly fine. That path may work great, splendidly, right? We hit all these things and the code works great. But a different path through the same code, which doesn't have foo be true, this condition is false. What bad thing might happen? It's a null pointer assignment, right? We have this going on, right? And it hasn't been initialized. It's only when we go this way that it's been initialized. If all we're trying to do is reach all states, hitting here, we're done, right? But we've missed this key error where if we don't go through this, wend through it in the right way, we're not going to get to that point. And as a result, p head will be null, and assigning this will be assigning through a null pointer, and bad things will happen, right? Somewhere I heard that the Roman Empire fell because they didn't handle the null pointers properly, but that's not the case. Especially given the performance on the estimation quiz, I should push that. So there were no null pointers in ancient Rome. Okay, so the next step up for this is transition coverage. This is edge-based testing. Here we're not trying to reach the nodes. We're not trying to reach the vertices in the graph. Or to use the low-level analogy, the statements. We're trying to reach the branches, right? We're trying to reach the transitions, okay? The edges in the diagram. And here we may have many test paths that will cover a particular edge, but that's not the point. The point is we need to cover all the edges. We want to cover all of the different particular branches through the system, okay? And we're going to need to find a particular test case that exercises a given path. And sometimes we'll have to watch out and reject paths that are impossible, that we can't possibly get to. So what I highlighted earlier, and I kind of flashed it up and didn't dwell on it, was this graph. And this is called subsumption hierarchy. I mentioned last time that in some of your courses, I think 364, how many people have taken 364 or are taking it? Good decision, yeah. Some of you may have encountered in 360 as well. Machine hierarchy, Turing machines, push-down automata, finite state automata. And there's a corresponding hierarchy in things like regular expressions, context-free grammars, general programs. Okay. In one case, it's sort of the things that consume it. The other case, it's things that sort of express the rules for it. We have this hierarchy. Anything that can be done by a finite state automata can be done by a push-down automata. Anything can be done by a push-down automata can be done by a Turing machine. But Turing machines can most assuredly, most avowedly, do things that push-down automata cannot do. And push-down automata can do things that a regular expression cannot do, like match parentheses, nested sets of parentheses, right? So there's a notion of subsumption. The Turing machine subsumes what can be done by push-down automata. So it is with edge coverage or transition coverage. It subsumes node coverage. What do I mean by that? Well, in a given program, if we achieve transition coverage, edge coverage, we will almost assuredly achieve coverage in terms of statements. One of the reasons I put in the wiggle room of almost assuredly is, okay, if there's a block of code where there's no transition to it, then you will not cover it, but neither can you get to it with statement coverage anyway. So it's kind of a moot point. But the point is, edge coverage is strictly more powerful. And maybe you see where this is going, because it's not at the top of the diagram. We're going to go up to here, okay? This one, I would argue, is of less practical interest. Why not complete path coverage? Why can't we say, well, edge coverage, what piddling nonsense is that? I want to achieve complete path coverage. I want to cover all possible paths through the program, all possible ways the system could go through the program. Why is that typically totally infeasible? A pipe dream. Why?
Any combinations of paths?
Okay, so there's many combinations. There's a huge number, but it's actually something more extensive than that. Why? It's more impractical than that. It's like the difference between computability and complexity. If something's uncomputable, it's impossible at a deeper level than if it's simply intractable, meaning it would take a very long time to do it. Yeah. Yeah, and it's true it's not scalable, so that's good. But it turns out that complete path coverage, that would be like saying, okay, on the system, I want to have at least one test case that will exercise the case where the loop doesn't go at all. That it has while such, and it just falls through because it's not true at first. And once where it goes once, and once where it goes twice, and once where it goes 3 times. And generally speaking, we can't exhaustively test that because there are many systems where there's no limit to the number of times you can go around that loop. Think about the Unix command line, right? Linux command line. Can you exhaustively test all possible commands that could ever be given? No, because it could be arbitrarily long. We can't possibly test all possible paths. It's we could start working towards it. But if you could achieve this, you could solve the halting problem. For whom that's the people in the room prove that's a meaningful statement. We could determine if we have demonstrated that this program works correctly under all possible numbers of iterations of loop, arbitrarily many. We can prove that it works correctly. We can prove whether or not it's ever going to halt by putting something after the loop, for example, or within the loop once it reaches a certain number, be able to that it will halt. And we could always guarantee, okay, it's not going to halt, so therefore we know it passes the test. So in short, achieving complete path coverage is completely impossible. But we can do something that's pretty good, and that's called prime path coverage. And we're going to be coming to that next time. Okay, let's continue to talk, though. Transition coverage, it's a sensible thing. And Mahmoud told me, I didn't realize it now, but apparently Istanbul now can achieve transition coverage. It can achieve coverage of branches, which is a big step forward compared to many past frameworks, which were limited to statement coverage. So here, instead of just going and reaching the states and saying we're done for the day, we're going to fill in the missing pieces. Where are the big missing pieces? The things that will be hard to pass the red face test. It'll be hard to honestly tell your manager, yes, the testing has been really thorough, unless you filled in what gaps here. Where are the big gaps? Let's assume this path goes through give ticket. Where are the big gaps? Exactly. Yeah. Okay, so you're saying your system is really tested, but you've never actually tested that it properly refunds someone who's paid but wants to cancel it? I mean, come on, come on. Or a case where it's been ticketed, but the ticket has been returned, where it's a paper ticket and cancelable customers. I mean, it lacks a certain plausibility to say it's been thoroughly tested. And transition coverage guarantees that, right? Yes, it reaches all the states, but it also reaches all the states by the different methods by which you could reach them. That is the type of English up with which I will not put. But I'm afraid it's out in the ether now. Okay. So here we have to cover each transition between states and blocks. In some cases, it's transitions that occur at the level of low-level operations. So, for example, for this, we would cover every one of these branches. I think that's what Mahmoud is mentioning Istanbul is achieving. It's achieving each branch, or it's judging you. It's not achieving it. It's judging the degree to which you have covered each branch. It's quantifying your level of coverage in terms of branches, which at least clues you into the fact that you haven't done due diligence yet, but because you've missed a certain, 30% of branches or something, which is really valuable. But here we would be covering these transitions between basic blocks. You see those? Yeah. So we'd be seeking to cover those. Not merely that we've reached this block at least once, but we've gotten, for example, to this block, L, from H to L, also from I to L, also from E to L, and F to L. We've come all of those different ways. It's not till we've achieved that we say we've achieved transition coverage. It's a lot stronger condition than just saying, oh yeah, I reached L at least once. You appreciate that? So, ladies and gentlemen, here we're going to need a set of test cases that will not merely achieve the fact that we reach all these different blocks. I mean, that's good, right? That's a good start. If every team here achieved guaranteed coverage in terms of the nodes, the vertices here, I'd sleep better. I feel good. I feel pretty good. If you can achieve transition coverage, that you've not only reached this screen of your application, you have at least one test that reaches this screen. I don't know how good I'd feel. I'd say, yeah, okay, tell me more, right? But if you say, I've reached that screen from all the different ways, we've reached it after an error from this previous screen, we've reached it after a correct transition, we've reached it from a notification sent to the user or whatever, I'd say, okay, now you're talking. So, if you're able to get transition coverage, I'd say, okay, you're going in the right direction. This is really good. Okay. Now, it's not perfect. At least we will have caught this case. Why would we catch this case? This was missed for state coverage, but why would we catch it for transition coverage? This is a statement. Statement coverage, as long as we reach this, this, and this, we say we're done. As long as we have one test case that reaches all three of those, at least one that reaches each of them, we'd say we're done. And so we could have one that just goes here, 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 and we say we're done. And we missed this case of the null pointer. But with transition coverage, what is transition coverage going to get us to do? It's going to force us to handle what cases? Louder.
Getting to set retail when foo is null.
Yeah. So we're going to test when foo is true. And we also, so that's when it will go this way, go into the consequent. And we're also going to be testing it for the other branch, which goes directly down here. It skips it, right? That's another transition when foo is false. And that case may, probably in this case, would uncover this null pointer exception. Do you understand that? Okay. So transition coverage is at a practical level considerably stronger, but it's not perfect. For example, if you have combinations in here, combinations of possibilities, right? Maybe you test, okay, when foo is true, test when foo is false, you test when bar is true, you test when bar is false. But you're not testing all possible combinations of foo and bar, you know, and maybe these two if statements interact in kind of a funky way that an error only comes up if foo is true and bar is false or something like that. Sometimes these things can happen with combinations of conditions. And transition coverage is not guaranteed to spot gaps that can lead to that. But at least it's spotting, you know, the biggest gaps, right? And it turns out there are stronger forms yet where you talk about transition tuple coverage. Okay, I'm not merely covering all transitions. I'm not really reaching all transitions. I'm reaching all pairs of transitions. It turns out that gets more complicated. There's few tools that support it, and it can be logically impossible. You know, maybe, for example, bar is in fact logically only true in a subset of the times where foo is true, and it's never true otherwise, right? Or something like that. You're not going to be able to exercise all possibilities because only some possibilities are logically possible. And you'll see this even in diagrams like this. So I've shown here transition coverage for this diagram with 3 paths, 4 paths: blue, green, yellow, and red. So 4 ways through this diagram, and I am covering all of the different mumble. Successful repair should also be covered there, I think. Yes, there's a missing one there. Other than that, I think I'm covering all of the transitions, but I'd argue there's a latent problem here. Why is there a latent problem? This model, this abstraction, is a simplification of the world. It's simplifying certain types of information out. And I'm saying I want to take these paths. Why is it problematic? Well, you notice the red path. I'll cut to the chase here. You notice the red path. Up here, it's going through a transition that's contingent on being a US or EU resident. Meanwhile, that red path continues on to go on a transition where it's not a US or EU resident down here. So there's a logical contradiction here. On the one, we can't have our cake and eat it too. On the one hand, we're saying it's restricted to US and EU residents here. We're saying we're neither. It's not logically possible to achieve that path. We need to go back to the drawing board with the red path and come up with some other combo of paths where maybe one of them would take a different path up here at the top. Instead of going 0 to 3, maybe it would go, 0 to 5, and then come down with this path to 9. And we'd need a different, and we'd have to have a different path. In fact, there is one, the yellow one, which exercises 0 to 3 and the 3 to 5. So in short, we may think we have paths, but then when we really think through the possibilities, we can't make it happen. We cannot make it, we cannot achieve that. And that's the sort of challenge that you folks are going to come up with. When you come up with concrete test cases, you may realize, oh, wait, we want to do this with a single test case. We can't. We actually need more than one concrete set of input to achieve this coverage. We thought we could hit this, this, and this in the same path. Cannot do. We need several different test cases. That's what you have to come up with. Concrete test cases that are going to exercise it. And sometimes you realize, oh, the graph is imperfect. It doesn't allow us to, reasoning just about paths in the graph isn't enough. We have to come up with a test case that's logically feasible. Okay. So I'll finish some remarks on that next time, and then we'll talk about prime path testing, this kind of highest level of testing, prime path coverage up here. We'll talk about how that's performed next time. Thanks very much.
What are you gonna do?